Welcome to AI Paper Podcasts. We dive into important research papers, break them down, and give you the insights you need to stay current.
That's right. And today we're looking at a really interesting one that tackles a problem familiar to anyone working with mobile robots.
Yeah, this is about sensor fusion. Specifically, how do you make sense of like half a dozen different sensors, maps, maybe GPS?
And they're all telling you slightly different things about where the robot is, right? And worse, their reference frames, their internal maps, are constantly drifting apart. It's a fundamental headache.
Exactly. So the paper we're discussing presents a framework called holistic fusion, or HF.
And the name really fits. It's about building a state estimator that doesn't just fuse data points, but actively manages the messy relationships between all these different coordinate systems.
Okay, so for everyone who needs the super quick version, maybe for that short form content clip, here's the 1-minute rundown on holistic fusion.
Right. The core idea. HF is an open source framework. It's designed to be really general, task agnostic, platform agnostic for robot localization and state estimation.
And it's big innovation. It tackles fusing inputs, think absolute positions from GPS, local odometry, maybe from LiDAR or wheels, landmark sightings, even when these inputs come from different coordinate frames that aren't fixed. They drift.
Yeah, that drift is the killer problem usually.
Right.
HF's breakthrough is that it stops treating these frame misalignments as just noise you try to filter out.
Instead, they make them part of the solution.
Exactly. They formally include the transformations that align these arbitrary local reference frames back to a global world frame. And these transformations become dynamic variables within the optimization itself.
So the alignment itself is being solved for continuously.
Precisely. And the key mechanism for handling the drift, like your LiDAR map slowly sliding relative to the GPS frame, is they model this drift, this evolution of the frame alignment, as a multivariate random walk.
Okay, a random walk. So it allows the frames to shift over time in a probabilistic way.
Yep. By putting the robot state, sensor calibration parameters, and these drifting frame alignments all into one big factor graph optimization.
They managed to get the best of both worlds.
That's the goal, and they show it works. You get simultaneously really smooth, low-latency local odometry, which you absolutely need for control.
And you also get low drift, globally accurate localization for planning and high-level tasks.
And they demonstrated this isn't just theoretical. They deployed it on 3 very different robots. The animal quadruped, a fast off-road vehicle called Racer, and even a big construction excavator, HAP.
Wow, okay. That's a solid range. So that's the high-level pitch.
Yeah.
Now let's dig into the details of how they actually built this thing.
Sounds good.
So before holistic fusion, maybe let's set the stage a bit more. Why is this sensor fusion problem so tricky, especially the conflict between local smoothness and global accuracy?
Well, think about what different parts of the robot system need for low-level control, like walking for a quadruped or, stabilizing a drone.
You need state estimates coming in super fast, maybe hundreds of times a second.
Exactly. And they need to be incredibly smooth and locally consistent. We often call this the odometry frame estimate. If that estimate suddenly jumps or has jitter,
your robot falls over, or your drone flies erratically, bad news.
Right. But then you have high-level tasks, path planning over long distances, or maybe a construction robot interacting precisely with the site plan.
For that, you need to know where you are in the world accurately, relative to some global map or coordinates. That's the world frame estimate.
And the traditional methods, they really struggle to deliver both perfectly. A key reason, as the paper points out, is dealing with the disparities across incoming measurements.
And it's not just the obvious stuff like some sensors being faster than others or data arriving out of order. We have decent solutions for those now.
Yeah. The real sticking point is the reference frame disparity. Imagine you have your IMU, right? Then you have maybe a LiDAR SLAM system running.
And a visual SLAM system, maybe even wheel odometry.
And each of those SLAM systems, or odometry sources, basically creates its own little map, its own coordinate system. And critically, these coordinate systems aren't perfectly aligned with the real world or even with each other.
And they drift over time due to accumulated errors.
That's the killer. Your LiDAR map might slowly rotate or translate relative to the true world frame defined by, say, GPS. You can't just calculate a fixed offset at the start and assume it holds.
Which makes sense why the HF paper lists those 5 objectives, O1 to O5. O1 is basically demanding both the smooth local O frame estimate and the accurate global W frame estimate.
Right. And O2 handles the practicalities of delayed out-of-order data. But O3, that's really the core innovation we talked about.
Hmm.
The automatic alignment and synchronization of all these diverse drifting reference frames. They call it localization management.
It's like the system's not just using the sensors, but actively managing their contexts.
Exactly. And for anyone listening who actually builds robots, O4 and O5 are crucial too. It supports automatic extrinsic calibration, figuring out how sensors are mounted relative to each other, and it's designed to be easy to adapt. You don't want a solution that only works for one specific robot setup.
Yeah, generality is key if this is going to be widely adopted. Okay, so let's get into the mechanics. How does the factor graph actually work? They use MAP estimation, ISAM2. It sounds fairly standard for modern state estimation.
The backend solver, yes, ISAM2 is a common choice for incremental smoothing, but the magic is in what they put into the state vector being optimized.
Usually that state vector is just the robot's pose, velocity, maybe IMU biases,
Yeah.
the navigation state.
Right. HF goes way beyond that. They introduce what they call dynamic context variables, represented by theta, which are specific to the setup and the environment. It's not just about the robot anymore.
So what kind of context variables are we talking about? They break it down into categories.
Yeah, three main dynamic types beyond the standard robot navigation state. First, there are dynamic landmark states.
Like features in the environment.
Exactly. For the animal walking robot example, this could be the estimated 3D positions of stable footholds it's detected on the ground. That's crucial information for the walking controller, and it makes sense to optimize its estimate alongside the robot's own pose.
Okay, makes sense. What's the next category?
Dynamic global time invariant states. This is mostly for things that don't change often but still need to be estimated or refined. The prime example is sensor extrinsic calibration, the fixed rotation and translation between, say, your IMU and your LiDAR.
So it can fine-tune sensor calibrations online. That's useful.
Definitely. But the absolute core, the real novelty, is the third category, dynamic reference frame alignment states.
Okay, this sounds like where the drift problem gets tackled.
This is it. These variables represent the transformation, the rotation and translation needed to align any arbitrary local reference frame, like your LiDAR, map frame, R sub I, with the global world frame, W, at a specific time, K.
So instead of trying to fix these alignments beforehand or using some external process,
They become variables inside the main optimization problem. The graph solver is constantly estimating the best alignment transformation based on all available sensor data.
so the relationship between the LiDAR map and the GPS world isn't fixed. It's an outcome of the optimization.
Precisely. It's estimated alongside the robot's pose. They're managing the system's context within the state estimation.
And it sounds like it can handle various measurement types feeding into this graph.
Yeah, the paper mentions four main categories their graph creation algorithm supports. IMU pre-integration factors, absolute pose measurements like GPS or mocap in any frame, feature landmark observations, and local or relative measurements like wheel odometry or scan matching between LiDAR scans. It's built to be flexible.
Okay, let's zero in on that drift issue again. You mentioned they model the alignment drift using a random walk. Why was that necessary? Why not just say, align the LiDAR map to the first good GPS fix you get, and then just trust the LiDAR odometry from there, applying that initial fixed offset?
Because fundamentally, that local LiDAR odometry will drift. No sensor is perfect. Over time, small errors accumulate, and the map generated by the LiDAR will slowly slide and rotate relative to the true world.
And a single fixed alignment transformation calculated at the beginning just gets more and more wrong over time.
Exactly. The paper explicitly calls out simple alignment methods like the well-known Umeyama alignment.
Right. That finds the single best rigid transformation between two whole point clouds or trajectories. Good for comparing results after the fact.
Good for post-processing, exactly. But totally unsuitable for online estimation where one of the frames is continuously drifting relative to the other. They show some plots from real hiking data where using a static alignment just leads to massive errors accumulating over distance compared to HF.
So the random walk model, how does that mathematically let the system cope with this continuous drift within the factor graph?
Okay, so the state variable isn't just the alignment transformation itself, but also its change over time. The random walk model basically says that the change in the alignment transformation from one time step to the next is, on average, 0, but it has some variance. It follows a normal distribution around 0.
So it assumes the drift is random and accumulates over time, rather than being a fixed offset or a predictable bias.
Pretty much. It allows the estimated alignment transformation, the relationship between the local map frame and the world frame, to evolve, to sort of wander slightly at each time step.
Ah, so the optimization is constantly making tiny adjustments to the alignment transformation to keep it consistent with incoming global measurements like GPS, while respecting the fact that the local source, like LiDAR odometry, is generating the relative motion.
Exactly. The random walk acts like a soft constraint, allowing the alignment to adapt to the slow drift, preventing the kind of large errors you'd get with a fixed transformation. The variance of the random walk basically tunes how much drift you expect.
Okay, that makes sense for handling the drift itself. But they mention another problem that crops up when you start dynamically optimizing these transformations, especially rotations over large distances. Something about numerical stability.
Yeah, this is a really practical issue. Imagine your robot has traveled kilometers away from the origin of the global world frame, maybe where the GPS system is centered. Now you're trying to optimize the orientation part of the alignment transformation between your local LiDAR map and this very distant world origin.
A tiny error in rotation around that distant origin
Results in a huge translational error way out where the robot actually is. The paper calls it the massive lever arm problem. It makes the optimization problem numerically very sensitive or ill-conditioned. Small measurement noises can lead to huge jumps in the estimated state.
Okay, that sounds bad. How did they fix that?
They introduced a mechanism called local keyframe alignment.
Local keyframes. How does that help?
Instead of always relating the local sensor frame directly back to this single, potentially distant global world origin, they do something clever. Whenever they need to create a new reference frame alignment variable in the graph.
Like when a new sensor comes online, or maybe after traveling a certain distance?
Right. They also generate a new local keyframe node in the graph, which is anchored near the robot's current position, but expressed in the world frame. The alignment optimization is then done relative to this nearby keyframe, not the distant origin.
Ah, so the lever arm for the rotation is now much shorter, just the distance from the robot to the local keyframe, not all the way back to the world origin.
Exactly. It makes the optimization much more stable and robust, especially for long-duration missions over large areas. It's a way of keeping the optimization numerically well-behaved by performing adaptations locally.
That's quite elegant. Okay, structure seems solid. Let's talk about performance. Factor graph optimization, especially with all these extra variables, sounds computationally heavy. How do they run this in real time and get the high rate updates needed for control?
Yeah, you definitely can't run the full optimization at, say, 400 hertz for IMU rates. So they use an approach that's become fairly standard in high-performance estimators, an asynchronous prediction update loop, meaning you have two loops running. One is super fast, running at the full IMU rate. It just takes the last optimized state and predicts forward using the IMU measurements, basically, dead reckoning for a very short time.
Okay, so that gives you continuous state estimates at high frequency.
Right. Then, in a separate, slower thread, the main factor graph optimization runs. They use ISAM2, which is incremental, so it doesn't recompute everything from scratch. It incorporates all the new sensor measurements, maybe slower camera frames, delayed GPS fixes, LiDAR scans and computes, and updated optimized state.
And when that slower optimization finishes, it corrects the state being used by the fast prediction loop.
Exactly. The update from the background optimization corrects the trajectory. But this brings us back to that critical O-frame, W-frame split.
Because if that background optimization gets, say, a GPS fix that realizes the robot is actually a meter off from where it thought,
the optimized world frame estimate, W, has to jump to reflect that correction. That's necessary for global accuracy.
But if that jump directly feeds into the local odometry frame used for motor control,
disaster. The robot lurches. So HF has a mechanism to guarantee that the O frame remains smooth even when the W frame jumps.
how do they decouple them?
When the background optimization provides an updated state, they don't just slam that new global pose into the O-frame. Instead, they look at the change the optimization made. They calculate the implied local motion increment, basically, the small step plus one the robot took in its own body frame between the last two IMU steps, according to the newly optimized trajectory.
So they extract the smooth, corrected relative motion.
Yes, and they integrate that smooth relative motion back into the local odometry frame estimate. Crucially, they also make sure the velocity estimate in the O frame remains smooth, often by taking the velocity from the optimized W frame estimate, which incorporates information from all sensors over a longer horizon.
So global position jumps for accuracy. But local pose and velocity evolve smoothly for control.
That's the guarantee. And the results bear it out. They highlight the animal hike experiment beta, tough forest trails, stodgy GPS.
Yeah.
The HF odometry output had literally 0 jumps recorded, NOJ number of jumps. And the rate of change of acceleration was significantly lower than baseline methods. That smoothness is exactly what you need for controlling something like a walking robot.
Okay, that's compelling evidence for the smoothness.
Yeah.
Let's broaden out to the other real-world examples they use to show this thing is general. The animal hike seemed key for validating the core fusion and drift modeling.
Absolutely. Just using the LiDAR odometry on its own gave an absolute translation error, 8AE, of about 1.35 meters over the hike.
Which is decent, but not great.
Right. But when HF fused that with the filtered GNSS data, the 8AE dropped way down to 0.31 meters. That's a huge improvement.
And they tested disabling the random walk.
Yes, crucially, they showed that if you turn off the random walk drift modeling, if you try to use a fixed map-to-world transformation, the fusion basically breaks down and the error blows up again. It proved that modeling the drift wasn't just a minor tweak, it was essential for making the fusion work robustly in the real world.
Okay, solid validation there. What about the racer vehicle? That one had, what, 5 different sensors?
Yeah, IMU, GNSS, LiDAR, radar, and wheel encoders. A complex setup. Here, the interesting result wasn't just the final localization accuracy, but how HF functioned as that localization manager they talked about.
How so?
They specifically used HF to estimate the transformation between the global world frame from GNSS and the map frame being generated by their LiDAR inertial odometry LIO subsystem.
So estimating text LIO directly.
Exactly. And the transformation sequence they got out of HF was significantly smoother and less noisy compared to trying to calculate that same transformation manually, like by just taking the difference between the LIO pose and the GNSS pose at each step.
Which makes sense. HF is using all the sensor data and the motion model within the optimization to estimate that transform.
Right. For a fast vehicle, having a smooth, stable estimate of how your local map relates to the world is really important for planning and control consistency.
Okay, and the final test bed, the EKP excavator. This sounds like a long-term torture test.
It really was. Multiple days of operation on a construction site. These environments are tough, long, lots of metal, potentially blocking GPS, and often geometrically degenerate, meaning the shape of the environment doesn't give the LiDAR enough features to localize reliably on its own.
So perfect conditions for drift to accumulate.
Exactly. And what they showed was, first, the system remains stable over these long durations, thanks in part to that local keyframe alignment we discussed.
And
Second, they looked at the estimated drift itself, the magnitude of the random walk corrections being applied to the LiDAR map's alignment. And they found that this estimated drift actually increased precisely when the excavator was moving through those geometrically degenerate areas where the LiDAR quality was expected to be worse.
So the system itself recognized, through the optimization, that the uncertainty in the LiDAR map's position was growing, and it allowed the alignment to drift more to compensate, consistent with the other sensors like the IMU or intermittent GPS.
Precisely. It's a validation that the random walk model isn't just smoothing things out, it's actually capturing and representing the time-varying uncertainty and quality of the different localization sources within the single optimization framework.
That's really cool. It adapts to the quality of its inputs implicitly.
Yeah. So overall, I think Holistic Fusion really delivers on its promise of a more general, flexible architecture.
It seems the big idea is tackling the messiness of multiple drifting coordinate frames head on.
Absolutely. Instead of treating it as an annoying pre-processing step or a source of noise, they elevated frame alignment and drift into first-class citizens' dynamic state variables within the core optimization. That's the conceptual leap.
And making it open source, C++ area, based on GTSM. That clearly signals they want people to use this and build on it.
Definitely aims to fulfill that O5 objective of usability and adaptability. It provides a really strong foundation.
It really forces you to think differently about what belongs inside the state estimator versus what's treated as external context.
Right. They brought context, the relationship between reference frames, into the state itself.
Which leads us to the final thought for you, the listener. If HF shows we can successfully model and optimize context variables like drifting frames within a factor graph.
Mm-hmm.
What else could we bring into the fold?
Yeah, think about other things we currently handle with heuristics or separate modules. Could we, for instance, explicitly model environmental factors like geometric degeneracy as a variable within the graph?
Or maybe incorporate learned priors about expected motion or sensor behavior directly into the optimization factors.
Hmm.
How far can we push this idea of making the state estimation truly holistic by turning assumptions and external factors into explicit, solvable parts of the problem?
Something to chew on. It definitely opens up interesting possibilities for making robotic systems even more robust and generally capable.
Well, that was a fascinating look at holistic fusion. Thanks for walking us through it.
My pleasure. It's impressive work.
And thank you for joining us on AI Paper Podcasts. We'll catch you on the next one.